Hello, everyone. Thank you for joining our webinar. We're super happy to be here with you and share with you today a few latest AI-driven satellite solutions to help you better drive your business growth. Before we start, please allow me to introduce our speakers and agenda today. For speakers, we have Yusna, CEO of SpaceSense, Brianna, our remote sensing director, and myself as head of sales and marketing. During the following hour, Yusna will update you about the most recent advances that have been made in Earth observation and the values they represent for the agriculture industry. I will give you a brief overview of our product lines, and Brianna will show you our industry-leading Beyond Cloud solution in detail and its use cases. During this webinar, feel free to ask any question needed in the chat session below, and we will answer them during the Q&A session. Now, let's get started. I will hand over to Yusna.
Thank you, Enchi. I'm going to quickly share my presentation. Right. Yep. Okay, there you have it. All right. Yep, you see it. Great. So thank you, Enchi, for the introduction. Hello, everyone. I'm Jyotsna. I'm the CEO and co-founder for SpaceSense. So satellite imagery is not new, and satellite imagery in agriculture is not new. But now the latest advances in the three frontiers of space technology, big data, and AI are completely redefining what is possible for agriculture with satellite data. So today we have over 3,300 satellites, of which more than 900 are dedicated just for Earth observation. And this number is growing faster in the last 5 years than ever before, and it will continue to grow. In general, this has made satellite data available more frequently and at a much affordable price. Along with these numbers, the sensor technology that has made new solutions possible. For example, we are becoming more used to using multispectral data for crop monitoring, crop scouting, but also radar can help us know soil moisture everywhere on the field. And thermal infrared can also give you accurate field level temperature changes. And with multispectral, which is going to be a game changer in agriculture, especially for sustainable agriculture, it can be used to extract more than 10 different types of macro and micronutrients in the soil. So with these advanced sensors and the number of them, we are beginning to reach levels of accuracy and operational requirements needed for every day-to-day decision making. So combining these advances with AI and machine learning, we are today able to address use cases that could never otherwise imagine to solve. So some of them you will see shortly from Enchi, and even solutions that we could already solve today with the current available satellite images and AI, we have been able to make them more accurate at field level, yet scalable at global level, only because of machine learning and big data. And this approach and capability is at the core of everything we do at SpaceSense. Now I will pass over the presentation to Enchi to give you an overview of what we've been doing at SpaceSense.
Thank you, Yusna. Thank you for all these interesting insights. Let me get back to the slides. So here we go. Yeah, so now that you have understood these recent advances in Earth observation, I'd like to share with you how SpaceSense is concretely empowering agriculture decision-making with our three unique strengths. First of all, we apply machine learning to a combination of satellite imagery and ground truth data in an automated way. As a result, all of our solutions are easily adaptable to local environments at a global scale. Second point is that we are able to work with multiple types of satellite data, especially radar imagery. Our third specificity is that all of our data is provided via a very simple API system, which can be easily integrated to any existing infrastructure. So we currently monitor over 1.5 million hectares daily over 10 countries. And here are a few examples of our customers to whom we are delivering concrete values. We help them save cost and budget while taking their crop monitoring capability to the next level. We currently provide a fuller category of products, including cloud-free crop health data, variable rate application zoning tool, soil data, as well as a few tools for carbon sequestration monitoring. Now I will quickly go through them one by one, and feel free to leave a comment if you have any question on any of them. So if you are familiar with vegetation indices like NDVI, you must know that cloud coverage is a key issue in using them. Basically, when the satellite passes there and there are clouds, you will not get a new image for the field. So in fact, cloud covers up farmlands for over 50% of the time globally. It means that for crop monitoring, conventional satellite imagery is not a viable option and requires more microwave-based radar imagery. That is why and how we created our Beyond Cloud product. This solution is able to provide you cloud-free biomass data with a new crop health image every 2 to 3 days. And our remote sensing director, Brianna, will share with you in detail our methodology and walk you through a demo of this product later on. For variable rate application zoning is a tool that allows you to categorize any field into zones and based on up to 5 layers of input data. One key use case of this tool is that you could easily generate fertilizer or seeding prescription maps. Prescription maps allow you to help growers to optimize the amount of fertilizer or seeding input per zone in a given field. We are also working on a few soil insights. We have a soil moisture index, which gives you the moisture levels of the soil surface at field level. It allows you to obtain soil moisture data without the need to install any sensors. To be able to provide you a more accurate soil moisture information, we are also working on a sensor-like solution called soil moisture content, where we provide you soil moisture levels up to 30 centimeters depth, adapted to your region and the type of crop. To achieve this, we applied machine learning to a combination of ground sensor data and radar imagery. With radar imagery, you can also detect soil texture. You can also detect the key soil properties for the first 30 centimeters of soil. And that is how we created this soil texture model. Just like the soil moisture model, we use a combination of satellite images plus ground analysis samples as a way to customize the solution to the local soil. Last but not least, we also provide these 4 tools as third-party source of truth data for large companies interested in monitoring positive farming behaviors for carbon credits. We have crop rotation to see if a field is alternating in terms of planted crops. We have also cover crop to identify which field is using crops and when, cover crops and when, and crop type to detect which crop is growing where and when, and also tilling to monitor which field is tilled. Like I mentioned at the very beginning, we deliver all these data through a very simple API system, and we made the integration process the simplest in the market. So now that I have walked you through our different AI-driven satellite insights and their values, I'd like to hand over the presentation to Brianna. She will take a deep dive into our Beyond Cloud product.
Yes, thanks, NG, for that overview. And yes, now I'm going to present in more detail an example of an AI-driven approach to provide more insights for agricultural customers. So one huge problem that we face when we're using satellite data is cloud cover. And pictured here is an agricultural region in the northwest of France showing one vegetation index, NDVI, over a year. And what you'll notice is that for most images, you can't clearly see the field. In fact, in 2020, there were 150 satellite images from Sentinel-2, but only 30 were unaffected by cloud cover. And that means over 75% of the time, you won't be able to monitor these fields using satellite information. But that's exactly why we developed our Beyond Cloud product, which leverages machine learning techniques along with data from synthetic aperture radar or SAR satellites. So a very quick satellite remote sensing in 1 minute summary. Sensors on satellites detect different wavelengths of energy emitted from Earth, and traditional optic-based sensors rely on the sun as a source of energy. They record data from the visible and near-infrared wavelengths that are reflected back. And existing vegetation indices that you're probably used to rely on information from the red, green, blue, or near-infrared bands to give some information on plant health. But the issue with this approach is that it can't be collected during cloudy or nighttime conditions. But SAR satellites, on the other hand, emit their own source of energy, and they utilize microwave frequencies, which can actually penetrate clouds and allow data to be received even during nighttime conditions. So very similar to optic data, SAR also has different bands, which can penetrate different depths of the surface. But the type of data that we receive from SAR is very different. The data is very complex and reflects different scattering effects from the microwave signal. Depending on the surface type, the backscatter changes, and this allows us to derive and estimate physical characteristics, for example, plant structure. And that's the goal of our Beyond Cloud product, is to recreate these optic-based vegetation indices, but only using SAR data to provide more consistent data coverage and give better information about vegetation health. So the SAR-derived vegetation index that I'm going to be presenting today is going to be leaf area index, or LAI. And LAI is just a dimensionless parameter which characterizes plant canopies. So it represents the leaf area per ground surface area. We decided to start with LAI for two main reasons. The first is that it can be measured on the field, and it's often used to monitor growing cycles and also estimate crop yields. The second reason is that it's directly connected to the physical plant structure, and it can be used as a direct input to estimate biomass given the crop type. So because we're able to leverage field measurements of LAI, and because SAR is reflecting physical structures, we thought this was the best vegetation index to test our Beyond Cloud methodology. So our first step to build our model is to ensure that we can estimate LAI correctly using the optic data from Sentinel-2. So for this, we tested 3 different algorithms which estimate LAI, and we select the highest performing algorithm over croplands using a ground-based observation validation dataset from Copernicus. So specifically over croplands, we had over 90% accuracy using 2 of the empirical algorithms. And now that we can confirm that we can get decent LAI estimates using optic data, we can now train SAR imagery on this optic-derived LAI in a random forest regression model, and then apply that model in real time for any new SAR imagery that we receive. So I'm just going to give a small example of some of our model results. The first panel here shows LAI over some crop on June 15th, 2020, using the Sentinel-2 optic data. 2 days later, we receive an additional image, but it's hindered by cloud cover. That's why you see the leaf area index dropping to 0, and it's very noisy. But luckily, there's a SAR image available on the same date, and we apply our Beyond Cloud model to the SAR imagery. And what we see is LAI in the same order of magnitude, and even more impressively capturing some potentially lower performing areas of the field that we had observed in the optic data 2 days prior. We can also look at some field average LAI measurements over time. So here, the purple line that you see is LAI from the Sentinel-2 optic data. And what you'll notice is a lot of noise, and that's because of the presence of clouds. The red dots are the optic data that we have that are free of clouds, but you'll notice then we have 3 to even 4 month gaps between those measurements. The green line that you see is our SAR only derived LAI. And what you see is that it follows the growing season of LAI quite well, and it provides about 3 times as much more data availability. So we've established then that the SAR derived data can be used to provide more consistent vegetation monitoring, but we also know that fusing both the optic and the SAR data allows us to more accurately describe important dates for agricultural fields. So here's an example where we fuse the 2 data sets, both the SAR and the optic. We remove noise and we apply another machine learning clustering algorithm on the final time series. And the results here show much more clear and accurate signals for both sowing and harvesting dates. A quick example, if we had relied only on the optic data to, for example, determine the harvest date in late 2020, we would have estimated around the 1st of October, and we would not have received another source of data until December. But when we use the fused product, we actually see the harvesting date was 3 weeks later. So traditional techniques to also count crop rotations normally rely on estimating the maximum and minimum of LAI or NDVI. And that can make it very difficult to also track the crop rotations when the crop is varying or if there's a presence of cover crop. But using this same technique with the fused data set, we can actually more accurately determine the harvest and sowing dates independent of the cover crop or any crop type. And this is a time series where we have 2 different crops plus a cover crop present, and we're still able to detect the harvest and sowing dates accurately. So while we're very proud of our existing Beyond Cloud product, we always want to keep pushing the bar higher here at SpaceSense. And that's why we're also testing more computer vision-based approaches. So our next generation of Beyond Cloud, what we're working on now, is to consider the task of predicting LAI from SAR data as an image-to-image translation problem using a convolutional neural network or CNN-based model. The advantage of using this type of model is that it can potentially capture the LAI information, the spatial LAI information, and lead to less noisy output. That's because the CNN models look at images as a whole and not just individual pixels. So our Pix-to-Pix framework is a method to train image translation networks using conditional generative adversarial networks or GANs. And the advantage over the traditional training is that this method learns a custom loss for a given data set. So the figure here shows that we can use SAR data from Sentinel-1 to generate LAI using the Pix-to-Pix method, which depends on 2 CNN deep learning models. The first is a generator or a UNet, which is the image-to-image translation model. And the second is a discriminator, which is a model to learn that custom loss for the data set. So that concludes my overview of Beyond Cloud, and I'll pass it back to Unti.
Yeah, thank you, Verena, for sharing all these interesting details with us. And just before I continue, I will launch a poll for all our product lines now that you have a better idea of them. And let me get back to my screen sharing. Yeah. So right now here comes to the Q&A session. So please feel free to ask any question you have in the chat session below, and we will choose 5 of them to answer now and get back to you with the rest of the questions by email later. I saw that from among the audience here is already a few questions. First question, how do companies solve cloud cover issue today? I will give this question to you now.
Thank you, Anchi. Today, what we see in the agribusiness is to be able to have an image for, say, crop scouting or crop monitoring in a more reliable way. So to do that today, most companies that can afford are actually using very high resolution data only because they can have an image every day. So they have an image every day, and in the hope that within the next 4 days or 5 days, they have at least one image without clouds. And that's the strategy used by most agribusinesses that are trying to solve this problem. And the rest of them, they don't want to solve this problem. So they are managing with the clouded images, or they are not able to, either not able to afford the solution that is currently being used by these companies, or it's not an issue for them. So these are the two ways: either you solve it with a more expensive, high resolution image, or you don't solve it at all. This is how it's been doing so far.
Okay, thank you, Yusna. So I see another question. Can I use Beyond Cloud for Brazil, Brianna?
Yes, so the Beyond Cloud model is dependent on how many images we get from Sentinel-1. It depends on the overpass and where you're located. So here in Europe, we're lucky that it can come every 1 to 2 days. In Brazil, it's more closer to every 12 days. So the same methodology can be applied, but with less frequent data. No.
Okay. Yeah, here is one more question. When do you think you will be able to detect crop type and crop rotations? Yusna?
Yeah, sure. So we already have a solution for crop rotation. So irrespective of the crop type, we can already tell when a new crop is planted and when that crop is harvested. So crop rotation is something we can already do. So crop type detection, exactly, specifically, we don't have it yet, but it's something we plan to do in the near future.
Okay. One more super interesting question. What types of satellite imagery do you work with?
So I can answer that. So right now, we primarily focus on multispectral and radar satellite imagery, mostly in the medium resolution 10-meter range, purely because in terms of business case, it makes the most sense for agriculture. But that said, we have already worked with very high resolution image, like the ones coming from Airbus Pléiades, the 50-centimeter ones. But in the near future, we also plan to work with hyperspectral imagery as well.
Okay. Okay. And how do you, yeah, this one is super interesting as well. How do you guarantee your accuracy across, for Beyond Cloud solution, across different crop types? Brianna?
Yeah, and I think we also have another question in the queue that's a little bit similar. Someone's asking how many geographies is the Beyond Cloud product trained ready for? Is there a list of crops that it works with? So we always first try to create models that are more applicable for any variation of crop types. Most of our training is in Northern Europe and with the crops that are more familiar there. So winter wheat, barley, etc. And so it depends on what region you're specifically looking at. But we do have extensive validation data for the Northern Europe countries and also the crops common there.
Just to expand that on a little bit, so like Brianna said, when we build a solution, the approach in itself is to be able to cover all kinds of, to have something which is very much independent of the crop itself. The approach is quite independent. And then what we try to do is make sure this is very accurate, at least for the certain crops we know, and we can get validation data on the ground. So that said, we do it this way so that anytime there's a new crop we need to adapt to, or there's a new region we need to make sure this works there, it's rather simple to just expand to this new region, and with calibration or with new sets of ground truth we can get.
Yep. Okay. I think we have answered the 5 questions that we planned, and for the rest of the questions, we will get back to you through email to tackle all of them. Here comes now our webinar has come to an end. And thank you so much for joining us. We hope you find this session insightful, and we look forward to seeing you soon. Thank you so much. Bye.
Bye.